A brilliant streak of green light just sliced across the night sky, sending shockwaves through the scientific community. On July 1st, 2025, astronomers using the world's most advanced telescopes detected a strange object from beyond our solar system. This was 3I Atlas, only the third interstellar comet ever recorded, hurtling through space at breakneck speed, carrying secrets from a distant star system. A breathtaking image captured in Namibia in September 2025 revealed its coma glowing like a vibrant emerald, leaving the entire world to ask, what is this object, and why is it so unusual? Join me as we uncover the story behind the phenomenon that has the scientific world buzzing. The story began in early August, when 3I Atlas was spotted by scientists at leading observatories using instruments like the James Webb Space Telescope JWST and the Very Large Telescope VLT in Chile. Unlike typical comets that only wake up as they approach the sun, 3 Atlas exploded with activity at an extraordinary distance, far beyond the orbit of Jupiter. This object was not only moving at tens of thousands of kilometers per hour, but it was also highly active at 5 times the distance from the Earth to the Sun. That's 750 million kilometers away. Imagine a colossal snowball, larger than a stadium, racing through space and glowing brightly despite being so far from the Sun. This was unlike anything ever seen from a solar system comet. Its coma, the fuzzy cloud of gas surrounding its icy core, grew rapidly, and a distinct anti-tail, at least 56,000 kilometers long, more than the circumference of the Earth, became visible. You can picture it as an icy spaceship, leaving a magnificent trail as it blazes through the darkness. But what truly stunned scientists was another tail-like structure, pointing directly toward the sun, detected in early August. Just a few weeks later, by early September, this structure had transformed into a giant fan, as if the comet were spraying dust into the light. The color of 3I Atlas only deepened the curiosity. At first, it was faintly red, as if its surface had been baked by cosmic rays over billions of years. But by mid-August, its color shifted to a more neutral, whiter hue, as if a fresh layer of ice had been exposed. And then, in mid-September, astrophotographers Michael Yeager and Gerald Riemann, taking advantage of a lunar eclipse in Namibia, captured an image that astonished the world. The comet's coma was glowing a brilliant, otherworldly green, shining like a ghostly flame. You can see it clearly in these stunning images. But the strange part is, observations from the JWST show this color cannot be explained by any known mechanism. This is no ordinary comet, and it's challenging everything we thought we knew. Chemically, 3I Atlas is a bizarre treasure. Analyses from JWST and the VLT revealed it has a carbon dioxide CO2 to water ratio of 7.6 to 1, a figure never seen in any solar system comet. It also contains cyanogen ions, CN, and nickel vapor, but is conspicuously missing iron vapor, an anomaly, since iron and nickel are usually found together. Furthermore, the comet has almost no carbon chain compounds, like dicarbon C2, which are a key ingredient in many other comets. 3I Atlas is an ice ball with a completely alien chemical makeup, as if it came from another universe entirely. For comparison, let's look back at the 2 previous interstellar visitors. 1I Oumuamua, discovered in 2017, was a red, cigar-shaped object with no coma or tail. Yet it moved with a mysterious push, as if propelled by an unseen force. Scientists theorized it could be a nitrogen iceberg fragment from a Pluto-like dwarf planet. Meanwhile, 2I Borisov, found in 2019, was a more classic comet with a coma and tail, but it was rich in carbon monoxide, suggesting it formed in an extremely cold environment. 3I Atlas combines the strangeness of both. It's hyperactive, like Borisov, but possesses a unique physical and chemical profile that rivals the mystery of Oumuamua. Think of it as a cosmic traveler, carrying a story from a distant star system we've never known. And observations from the Nordic Optical Telescope also recorded a deep and narrow negative polarization branch, a rare feature indicating that the dust in its coma is pristine and unaltered. Orbital data from the Gaia Space Telescope revealed that 3I Atlas hasn't passed near any major star in the last 4 million years, with an estimated age of about 3 billion years, younger than the initial 7 billion year prediction. In the coming days, a coronal mass ejection, CME, is forecast to collide with the comet in late September 2025, which could light up the sky. Then, in early October, it will fly close to Mars, and by late November or early December, it will re-emerge from behind the Sun. Each of these events is a new opportunity to peer deeper into the mysteries of the universe. The discovery of 3I Atlas, along with Oumuamua and Borisov, in less than a decade, is a testament to the power of modern sky survey technologies like Pan-STARRS and the Zwicky Transient Facility ZTF. These instruments have turned rare finds into a steady stream of knowledge, opening a new era of interstellar research. 3I Atlas isn't just a comet, it's a window into the past of another star system. A cosmic fossil telling the story of planet formation billions of years ago. But what really lies behind its mysterious green glow and its extraordinary properties? Data from the world's leading telescopes is beginning to unravel the mystery. From its long-distance eruption to its unexplainable color, the scientific story of 3I Atlas opens a window into distant worlds where our familiar rules are challenged. Comets in our solar system typically begin spewing gas and dust only when they get close to the Sun, around 3 to 4 astronomical units AU, or 450–600 million kilometers away. This happens when surface water ice vaporizes, creating the fuzzy cloud we call a coma. But 3I Atlas became active much earlier, at a distance of 20 AU, or 3 billion kilometers, 4 times farther than Jupiter's orbit. Data from the James Webb Space Telescope, JWST, published in September 2025, revealed that the comet is overwhelmingly rich in carbon dioxide CO2, or dry ice, with a 7.61 ratio to water. Dry ice vaporizes at a much lower temperature than water, causing 3I Atlas to erupt with gas and dust while still deep in the cold reaches of space, like a frigid fire igniting in the cosmic darkness. This indicates it formed in the freezing outer edges of its home star system, where CO2 could condense into solid ice, giving us the first clue about the alien environment where it was born. The tail-like structure pointing toward the Sun, recorded in August 2025, was not an optical illusion like the anti-tails we sometimes see when Earth crosses a comet's orbital plane. Observations from the Gemini South Observatory confirmed it was a physical stream of dust, formed as the sunlit side of the comet heated up rapidly. The vaporizing CO2 ice violently dragged large dust particles with it, particles too heavy to be pushed away by sunlight into the long, 56,000-kilometer main tail. As a result, this dust streamed toward the Sun, creating a unique jet. By September, it had widened into a fan, likely due to the comet's rotation exposing fresh patches of ice to sunlight. A 2025 study from the University of Arizona highlights that this phenomenon reflects the dynamic surface of 3I Atlas, providing invaluable data on how interstellar objects react to solar heat. The surface of 3I Atlas is also covered by a thick, insulating crust, according to observations from the Very Large Telescope VLT in Chile. This crust acts like a shield, trapping water ice deep within the core and preventing it from vaporizing, leaving the CO2 ice to dominate its surface activity. As the comet neared the Sun, fresher, whiter layers of ice were exposed, explaining the color shift from red to neutral in August 2025. A University of California study from 2025 proposes that this crust formed over billions of years of exposure to cosmic rays, which oxidized the surface and created its initial reddish color. This reveals the comet's layered structure, hinting at a long journey from the outermost regions of its home system. The chemical composition of 3I Atlas is like a treasure chest from space, but filled with strange artifacts. Analysis from the VLT showed the comet contains cyanogen ions, CN, and nickel vapor, but lacks iron vapor and anomaly, as these two metals typically appear together in solar system comets. Furthermore, It is almost devoid of carbon chain compounds, such as dicarbon C2, a primary component of many local comets. A report from the Max Planck Institute for Astronomy in 2025 suggests this deficiency stems from unique conditions in the protoplanetary disk where 3I Atlas formed, perhaps in a region with very different temperatures or pressures. This challenges the notion that all comets deliver the same organic molecules thought to be necessary for life on early Earth. The brilliant green glow of the coma, captured during a lunar eclipse in Namibia, remains a baffling puzzle for scientists. Normally, this green color appears when dicarbon C2 molecules absorb sunlight and re-emit it, like a cosmic neon sign. But data from JWST, published in September 2025, confirmed that 3I Atlas is deficient in C2, ruling out this familiar mechanism, a flawed hypothesis. Popularized in a Medium post by Avi Loeb, suggested cyanogen CN was responsible for the green color. But a 1994 study from Cornell University had already disproven this. Cyanogen emits a violet light at a wavelength of 387 nanometer, near the ultraviolet spectrum, not green. Therefore, the color must come from an unidentified molecule. Discovering it could open a new chapter in astrochemistry, revealing previously unknown reactions in space. The light from the coma of 3I Atlas polarizes in an unusual way, a phenomenon recorded by the Nordic Optical Telescope in 2025. This feature, known as a deep and narrow negative polarization branch, indicates that the coma's dust is a pristine mixture of dark particles coated in a thin frost of water ice. A study from the University of Helsinki points out that this characteristic is similar to the dust on distant objects like Pluto or Charon, suggesting 3I Atlas could be a fragment of a dwarf planet or an ancient icy body from the fringe of its parent system. The polarization of light, like an invisible map, allows us to read this object's billion-year-old story. This not only clarifies its surface structure but also strengthens the idea that 3I Atlas is a cosmic fossil, carrying information about planet formation far beyond our solar system. These features, from its CO2-driven activity to the green glow mystery, show that 3I Atlas is a unique piece of the cosmic puzzle. Its strange chemistry challenges our models of planet formation, suggesting that star systems can have very different conditions. Its lack of organic compounds raises questions about the role of comets in the origin of life, while its polarized light opens a new way to study pristine objects from afar. But these discoveries aren't just about understanding 3I Atlas. They could change how we view the formation of planets and life across the cosmos. As we'll explore in the next chapter, Comet 3I Atlas, with its unique chemistry and anomalous properties, is more than just a fleeting spectacle in the night sky. It's a priceless artifact that opens a door to understanding how planets form across the universe. Findings from the James Webb Space Telescope and other leading observatories show that 3I Atlas bears the chemical fingerprint of a distant star system. With its dominant carbon dioxide, lack of organic compounds, and pristine dust structure, these features challenge all our familiar models of comets and planets, forcing scientists to rewrite the story of how planetary systems are born. But why is this object so important? And how will it change our view of the cosmos? The composition of 3I Atlas, rich in CO2 and poor in carbon chain compounds like dicarbon C2, acts as a cosmic fossil, preserving information about the conditions in the protoplanetary disk where it originated. A 2025 study from the University of Cambridge emphasizes that these differences show that other star systems can have vastly different chemical budgets and temperature gradients compared to our own, while current models often use our solar system as the standard. 3I Atlas forces theorists to build more generalized models that reflect the true diversity of protoplanetary disks throughout the galaxy. As a result, it is pioneering a new field, interstellar comparative planetology, where objects like 3I Atlas become the bridge to understanding distant worlds we can't observe directly. This makes 3I Atlas a turning point, not just a comet, but a key to decoding the architecture of the universe. In the field of astrobiology, 3 Atlas raises a profound question about the origins of life. Comets in our solar system are widely believed to have delivered organic molecules, like carbon chain compounds, to early Earth, contributing to the formation of life. However, the lack of C2 in 3I Atlas, confirmed by the Very Large Telescope VLT, suggests that not every star system provides the same prebiotic ingredients. A 2025 report from the SETI Institute proposes that the potential for life to arise may strongly depend on a star system's initial chemical inventory, enriching our understanding of the various pathways to life in the universe. Therefore, 3I Atlas not only tells the story of its parent system but also lays the groundwork for exploring whether life is common in the galaxy. The impact of 3I Atlas will reverberate for decades to come. In the next 5–10 years, it will drive a surge in efforts to detect more interstellar objects, leveraging next-generation telescopes and rapid response observation techniques like spectroscopy and polarimetry. A 2025 study from Harvard University predicts that within 20 years, a diverse catalog of interstellar objects will allow us to classify planetary systems based on their ejected fragments, creating a galactic map of planet formation. These insights will not only clarify how planets are built, but will also reshape our search for life beyond Earth. But the bigger questions remain: how will these discoveries shape the future of space research? And what awaits us as 3I Atlas faces new cosmic challenges? The mystery of 3I Atlas is not yet fully solved, and the remaining questions are driving scientists worldwide. The location of its home star system remains unknown, as data from the Gaia Space Telescope can only trace its trajectory back 4 million years, not far enough to pinpoint its origin. Its estimated age of 3 billion years, younger than initially predicted, only deepens the questions about its formation history. The brilliant green glow of its coma, which is not linked to dicarbon or cyanogen, as confirmed by the 1994 Cornell University study, could arise from an unidentified molecule, opening the door to discovering new chemical reactions in the cosmos. These mysteries are not just challenges, they are opportunities to redefine our understanding of space. The study of 3I Atlas is a race against time, requiring tight coordination between facilities like JWST and the VLT. The green glow mystery also underscores the importance of accurate science communication. The flawed cyanogen hypothesis, once circulated in articles and on Avi Loeb's Medium blog, was refuted by spectroscopic data, illustrating how science self-corrects to pursue the truth. These challenges are not just obstacles, they are a driving force for the scientific community to accelerate discovery and ensure the public understands the value of cosmic visitors like 3I Atlas. As this comet continues its journey, what other secrets of the universe will it reveal? And how ready will we be to receive them?